As Java developers, we write our code in Java files, compile it into platform, independent bytecode, and then let the Java virtual machine take over. But what actually happens inside that black box? Today, we're tearing down the JVM layer by layer to see exactly how it loads, verifies, executes, and manages your application memory. Let's dive in. Think of the JVM as a highly automated runtime factory. Its responsibilities follow a strict lifecycle split into 4 major phases. First, it loads and verifies. It pulls your class files through the class loader subsystem and instantly passes them to the bytecode verifier to make sure the code is safe. Second is memory allocation. It routes data dynamically into dedicated runtime areas, like the heap, the stack, and Metaspace. Third is code execution. The execution engine uses a hybrid approach. An interpreter reads bytecode instantly for fast startup. Just-in-time compiler optimizes hotspots into native machine code for maximum performance. Finally, memory cleanup. The garbage collector automatically sweeps away unreferenced objects, keeping your system lean. To understand where your code lives, you must understand the big 3, heap, stack, and Metaspace. The heap is the global object kingdom. Every time you use the new keyword, that object and its instance variables live here. It's shared across all threads and relies entirely on the garbage collector to clean it up. The stack is thread, private and inherently thread safe. Every single thread gets its own isolated stack. It stores primitives, method local variables, and object references. Its life cycle follows a strict last, in first, out rule. When a method runs, a frame is pushed. When it returns, it is instantly popped and wiped out. Metaspace lives completely outside the Java heap in native RAM. It holds class metadata, method structures, and the constant pool. It stays alive as long as its responsible class loader is active. How do those classes get into memory safely? Through the class loader subsystem and the Parent Delegation Model. When your application needs a class, the application class loader doesn't load it immediately. It delegates the request up to the platform class loader, which delegates it all the way up to the bootstrap class loader at the core JDK level. The lookups then cascade downward. If the bootstrap loader can't find it, it passes the task down to the platform loader. If that fails, it falls back to the application class loader to scan your dependencies and class path. Why this complex hierarchy? Security. It prevents malicious code from injecting a fake version of core classes like java.lang.string. Before a single line of machine code executes, the bytecode verifier acts as the JVM's firewall. Because bytecode can be compiled anywhere or downloaded over a network, the verifier ensures structural integrity, type safety, and strict access control, blocking memory corruption bugs before they can happen. Once verified, execution begins, tracked microsecond by the program counter register. Think of the PC register as a private thread bookmark. Every thread has its own, storing the exact memory address of the current JVM instruction. When the operating system triggers a context switch, pausing thread A to run thread B, the PC register saves thread A's exact spot, allowing it to resume seamlessly later without losing data. Now let's talk about the production nightmares. Memory errors. A stack overflow occurs when a single thread pushes too many execution frames, blowing past its memory ceiling. The classic cause: infinite recursion without a terminating condition. An out-of-memory error Java heap space happens when the global heap runs out of room for new objects. This is typically driven by memory leaks, where stale objects are no longer needed but are still held by active reference chains, preventing the garbage collector from freeing up room. But what about out-of-memory error? Metaspace. This has nothing to do with the heap. It happens in native memory when application frameworks generate massive amounts of dynamic proxies at runtime, or when repeated hot reloads cause class loader leaks that completely fill your configured native space. Let's take a closer look inside a single stack frame. Every time a method is invoked, a new frame workspace is allocated containing 3 core elements. First, the local variable table, an indexed array storing the method's parameters and local references. Second, the operand stack, a workspace where bytecode instructions push and pop values to perform mathematical calculations and assignments. And third, the frame data, which holds resolution links back to the constant pool and handles return information so the system knows exactly where to hand back control when the method completes. Finally, let's address a classic misconception. Can calling System.gc guarantee that garbage collection will run? The simple answer is no. System.gc is a suggestion, not a command. The JVM reserves ultimate authority and will happily ignore the request if the heap has plenty of headroom. Worse yet, if the JVM does honor it, it typically triggers a full stop. The world GC, freezing all application threads and causing major latency spikes in production. This is why enterprise architectures often completely disable explicit GC flags to maintain smooth, predictable performance. Understanding the internals of the JVM turns you from a developer who just writes code into an engineer who can optimize systems and solve production issues with confidence. If you found this breakdown valuable, smash that like button, subscribe for more deep dives into enterprise system design, and drop your questions in the comments below. See you in the next one.